Welcome to Section 5.5, Properties of Quadrilaterals. Our objective is to identify the properties of parallelograms, rectangles, rhombuses, squares, kites, and isosceles trapezoids. For homework, we're going to work on page 244 to 248, 3 to 7, 15, 17, 20 to 21, 23, 27 to 28. So let's begin by talking about our parallelogram properties. Our first property says that opposite sides are parallel. So let's make out a parallelogram, and let's label its vertices P, A, L, and R. And let's go ahead and draw in what opposite sides are parallel would look like. PA would be parallel to RL, so we'll draw in the parallel arrows. PR is parallel to AL, so we draw our arrows there. Our next property, opposite sides are congruent. PA would be congruent to RL, and PR would be congruent to AL. So opposite sides are both parallel and congruent in a parallelogram. Next, opposite angles are congruent. My opposite angles would be angle P and angle L, angle R, and angle A. So those would be my opposite pairs of angles. Next, consecutive angles are supplementary. Well, if you think about consecutive numbers, it's one after the other. So consecutive angles are going to be angles that are right next to each other. Now, I'm going to draw myself a nice little loop out here. And I'm going to write down adds to 180 degrees. Now, to clarify what I mean here, angle P plus angle R is going to equal 180 degrees. Now, that would go for P and R and L and A and P. All my pairs of consecutive angles are going to be supplementary. Last but not least, my diagonals bisect each other. So I'm going to go ahead and I'm going to draw in my diagonals. There's one diagonal, and there's my other diagonal. Now, the diagonals themselves are not congruent. One's going to be longer than the other. But what they do is they chop each other in half. So the diagonal PL is going to be chopped into two congruent parts, and the diagonal RA is also going to be chopped into two congruent parts. And that's what a parallelogram is going to look like. Next comes our rectangle properties. Now, if we think back to yesterday's lesson, we talked about our quadrilateral family tree. And what we know is that a rectangle stemmed from a parallelogram. So all of our parallelogram properties are going to apply, plus some additional ones. Now, let's go ahead and let's draw in our additional properties first. First and foremost, in a rectangle, all of my angles are going to be right angles. So angle R, angle C, angle E, and angle T are right angles, which covers opposite angles being congruent and consecutive angles being supplementary. Next, what we have is that the diagonals are congruent. So let's go ahead and draw in those diagonals for my rectangle. There's one diagonal, and here's my other. Now, if my diagonals themselves are congruent, we know one of our parallelogram properties said that the diagonals are bisected as well, which means in this case we're going to end up having 4 congruent diagonal pieces, making different isosceles triangles. Now, let's draw in all those quadrilateral properties that apply to parallelograms as well that we don't have. Opposite sides parallel, opposite sides congruent, and are we missing any? Not that I can see either. So this is what a rectangle is going to look like. All right angles, congruent diagonals that are also being bisected, opposite sides congruent, and opposite sides parallel. Now I want you to look real carefully at these triangles. What I notice here is that I have 2 different pairs of congruent isosceles triangles. The left and the right, the top and the bottom. So just kind of make a mental note of that. So next we have our rhombus properties. For a rhombus, thinking back to our quadrilateral family tree, it stems from a parallelogram, so all of our parallelogram properties are going to apply. We also have additional properties that's going to separate it from being a parallelogram, starting with all sides congruent. So RH is congruent to RO, is congruent to OM, is congruent to HM. Next, diagonals bisect opposite angles. So let's go ahead and draw in our diagonals. Our first diagonal is HO. Our second diagonal is going to be RM. Now, what we learned from parallelograms is that opposite angles are going to be congruent. So the big angle R, angle HRO, is going to be congruent to the big angle M, angle HMO. Now, if the big angles were congruent and bisected, it's going to create a total of 4 congruent smaller angles that were formed. Same thing here. Angle RHM, our big angle, was congruent to angle ROM, our big angle. If it's congruent and bisected, again, it's going to create 4 congruent little angles. Next, the diagonals are perpendicular bisectors of each other, which means that we're going to have right angles formed. Now, they're also bisectors of each other. Unlike the rectangle, the rhombus's diagonals are going to be different lengths, but they still bisect each other, which means one of our diagonals is cut in half, and our other one of different length is also being cut in half. Now, I want you to take a look at these triangles, and I want you to notice something about them. What do you notice when you compare all 4 triangles? If you got it, make a little note of it. Last but not least, we want to kind of think about what properties of parallelograms we didn't draw into our picture yet. We have opposite sides congruent. We have opposite angles congruent. The consecutive angles are going to be supplementary, so we can make ourselves a little note here. What we're missing here is that opposite sides are still going to be parallel. And we're set. So next we get to our square properties. For squares, again, going back to that quadrilateral family tree, squares stem from a combination of rectangles and rhombuses, which stem from parallelograms. So all of our properties are going to apply. So let's take all those special properties and let's draw them in. Starting with all sides are congruent. That stems from our rhombus. All angles are right angles. That's going to end up stemming from our rectangle. Opposite sides are going to be parallel. That stems from our parallelogram, and we've seen that filter throughout. Now we get to the nitty-gritty. Let's draw on those diagonals. There's one diagonal, and here's my other. Now, the diagonals are going to be congruent. That stems from my rectangle, and they're also going to be bisected, which stems from my parallelogram, which means that we have 4 congruent diagonal pieces. Now, our diagonals are perpendicular bisectors. That stems from my rhombus, which means when they intersect, right angles are going to be formed. Now, as well as that, those diagonals are going to bisect my opposite angles. That again stems from my rhombus, which means that it's going to create congruent angles. Now, I want you to think about this. If you know that the angles were right angles, and they're being bisected, what does that mean about all 8 pairs of angles here? Hopefully you said that they're all 45 degrees, which makes them all congruent. And that's what a square is going to look like. Now on to our kite properties. Now, our kite properties. Kites were related to rhombuses in that it had half properties of rhombuses. Now, for a kite, what we have here is we have 2 disjoint pairs of consecutive sides congruent. So what that means is Ki would be congruent to Kt, IE would be congruent to Te. Now, does this mean that the top 2 and the bottom 2 are always going to match up? Definitely not. Remember, all these figures can be rotated. So it could be that you're looking at different pairs, such as Ki pairing up with IE if that figure was being rotated. Next, the diagonals are perpendicular. I gotta draw in my second diagonal. One diagonal was already drawn in for me. Here's my second one. My diagonals are perpendicular, just means again when they intersect, right angles are going to be formed. One diagonal is the perpendicular bisector of the other. We got the perpendicular part down. Now, the diagonal that's being bisected is the diagonal that's going to attach the vertices where the non-congruent sides meet. That diagonal is being bisected. Next, one diagonal bisects a pair of opposite angles. Now, the opposite angles that are being bisected, if you look at this top triangle and this bottom triangle, we'll see that they're isosceles triangles that were formed. The bisector that goes through the vertex angle of the isosceles triangle is going to be the angle that's being bisected. Now, those angles aren't congruent to each other, but they are being bisected. Last but not least, one pair of opposite angles are congruent. The pair of opposite angles that are congruent is going to be, if we look at this triangle, that's going to be a scalene triangle, the triangle that has three different sides. That big angle is going to be congruent to the other big angle. So angle KIE would be congruent to angle KTE. So again, it's going to be the angle that has the vertex where the non-congruent sides meet is the pair of opposite angles that are congruent. Now, kites are some of our most difficult quadrilaterals to kind of figure out. So these are some of our properties that we really have to look at and we really have to think about. Last but not least, we have isosceles trapezoid properties. For an isosceles trapezoid, we have legs that are congruent. Legs would be the sides that look like if you continued them, they would cave into one another. Secondly, bases are parallel. The parallel bases are going to be the sides that are going to attach those legs. Those bases should never be congruent, only parallel. Next, base angles are congruent. Now, we have two bases. The way this is oriented, we have a top base and a bottom base. The angles that are on the bottom base are going to be congruent, and the angles that are on the top base are also going to be congruent. Next, any pair of upper and lower base angles are supplementary, which means T and A are going to sum to 180 degrees. Angle R and angle P are going to sum to 180 degrees. Or if we matched up T and P or A and R, they're going to sum to 180 degrees. Now, last but not least, the diagonals are congruent. Now, unfortunately, I have no good way of drawing that in. But here we go. Instead of drawing it in here, let's just go ahead and write a congruency statement. Segment TP would have to be congruent to segment AR. They are not bisected, they are not chopped into thirds. The big diagonals themselves are just congruent. And that's what we have for isosceles trapezoids. Let's begin by doing a proof for our first example that goes with our special types of quadrilaterals. So let's go ahead and let's make a statement and reason chart. So first let's copy down those givens. That ABCD is a parallelogram. Now, you can absolutely go ahead and draw out that symbol, or you can write out the parallelogram. Next, angle GHA is going to be congruent to angle FEC. That's also going to be given. And let's draw in our tick marks. Angle GHA is congruent to angle FEC. Last but not least, HB is congruent to DE. HB is congruent to DE. That's also given. HB is going to be congruent to DE. Now, we're trying to prove that GH is congruent to EF. So my first thought here is try and get these triangles to be congruent to each other. Now, we want to use some of our parallelogram properties. So I'm going to go ahead and highlight over that parallelogram. So here's that parallelogram that I'm given. And one of my first properties that I think about when I see a parallelogram is that opposite sides are congruent. Now, the opposite sides that should be helpful to me is going to be side DC would be congruent to side AB. And our reason? Opposite sides of a parallelogram are congruent, which should be this full side here and our full side here. Now, if we know the big segment is congruent, and we know these little segments are congruent, the subtraction property allows us to say that the other little piece is going to be congruent. Segment EC is congruent to segment AH by subtraction. Next, look at my triangles, and so far I have 2 out of 3 pieces of congruency needed to state my triangles are congruent. Now, the other piece of information when I first think about a parallelogram is that opposite sides are parallel. And what I think about with parallel lines is those Z angles. In order to have those Z angles, which is what our alternate interior angles form, so I have to state my lines are parallel first. So let's go ahead and state that DC is going to be parallel to AB. The reason? Opposite sides of a parallelogram are parallel. Go ahead and let's throw our arrows in there. And now we're going to look for those Z angles. Now, the Z angles that we're looking for, use the parallel lines and a transversal. The insides of the Z's are going to be congruent, which should be this angle here and this angle here. So let's go ahead and state it. Angle ECF is congruent to angle GAH. The reason is if lines are parallel, then alternate interior angles are congruent. Now, looking at my triangles here, I see that my triangles have an angle side angle for my congruency. So let's go ahead and state congruent triangles. Triangle ECF is going to be congruent to triangle HAG. The reason is ASA, which means that GH is going to be congruent to EF by CPCTC. And we're set. Remember, in order to state that those alternate interior angles are congruent, you have to have those parallel lines first. So here we go, our last example. I went and saved the best for last. We're given that VRZA is a parallelogram, and I also let you know what all those different side lengths are going to be. We have the algebraic expressions 2x minus 4, 3y plus 5, 1/2 x plus 8, and y plus 12. Let's push pause and let's try and find out what the perimeter of our parallelogram is going to be. Now, here's what I did. I looked at what I have here with my parallelogram, and my first thought is that opposite sides are going to be congruent to each other. Now, that would mean that AV is going to be congruent to RZ, and it also means that VR is going to be congruent to ZA. So the first question that I ask you is, do I have a system? Absolutely not. Systems only happen when you have multiple variables in one equation. And what I have here is 2x minus 4 is going to equal 1/2 x plus 8, a single variable, axis. And on my other pair, 3y plus 5 is going to equal y plus 12. Let's go ahead, solve for x, solve for y. Now, if seeing that fraction makes you a little uneasy, let's get rid of our fraction. We're going to times absolutely everything in our equation by 2 and get rid of those fractions. So here we go. When I do that, I end up with 4x minus 8 equals 1x plus 16. And let's go ahead and solve. Let's subtract my x's from both sides. And let's add my 8 to both sides, which is going to leave me with 3x equals 24. Divide by 3, and x is equal to 8. For my next one, let's subtract my y to both sides. And let's subtract my 5 to both sides. That leaves me with 2y equals 7. Divide both sides by 2, which means y is equal to 3.5. Seems a little bit odd, so let's double check our work here. Now, let's take our x and let's plug it in. We get 2 times 8 minus 4, which is 16 minus 4, which is 12, and 1/2 of 8 plus 8. Half of 8 is 4. 4 plus 8 is also 12. My first set of opposite sides check out. Now, let's do my next set. 3 times 3.5 plus 5. 3 times 3.5 is 10.5. 10.5 plus 5 is going to give me 15.5. And for my next one, we have 3.5 plus 12, which again is 15.5. It checks out. Opposite sides congruent. So here we go. Let's go ahead and find that perimeter. Let's add up all those sides. 12 plus 12 plus 15.5 plus 15.5, which is going to give me a perimeter of 55 units. And we're set. Not as hard as we thought. So here's the answers to our homework. Again, it was problems 3 through 7, 15, 17, 20, 21, 23, 27, and 28. If you have any questions, please make sure you ask it tomorrow. And as always, have a good one.